We're recording. Okay, so like I said, because I can only use one side of the whiteboard and it would take way too much time to draw this out, we'll just start with sieve of Eratosthenes. So some of you have already seen this, but essentially what it is it's the fastest way to detect like what all of the prime numbers in a range are. If you're trying to find if one number is prime or not, then this will be slower. But like let's say like you can pre-process and you want to know what the first like 100 prime numbers are, or let's say you run this algorithm first, then you can find if a number is prime or not in constant time. So essentially like just like prerequisite knowledge in case you don't know, a prime number is a number that can only be divided by one in itself. So if we look at like 13, right, this is my dead marker. Also, can you mute yourself, Sebastian? Your keyboard's a little clicky. Thank you. So, basically, like if let me scoot this back. So if like we have like 13, if you try to pick any number that isn't like 1 or 13, it won't divide it. But if I pick like 8, like you could pick like 2 and 4, right? Thus 13 is prime and 8 is not. So so if we want to find like all the numbers that are prime or not, sieve uses a property saying that if a number is a multiple of a prime number, then it can't be a prime. So for example, we know that 7 is a prime number, but if we multiply 7 by 2 and we get like 14 or like 21 or something, then like we can break this up now into 7 and 2 or like 7 and 3. So any single multiple of a prime number cannot be a prime number. So we're going to use this property in sieve to like very quickly determine if things are prime or not. So by definition, 1 is not a prime number, so I'm going to go ahead and cross this off. Um, and now I'm going to go in order from the smallest numbers to the biggest numbers. And if I've reached something that isn't marked, then it means that it's a prime number. And I'm going to go ahead and cross off all its multiples. If something has already been marked, then it means that it's not prime and I don't really do anything. So it'll make a little more sense when I actually go through the examples. So let's start off here. So as I said, 1 is not a prime number, but now let's move on to 2, right? So 2 hasn't been marked by anything, so we know that 2 is a prime number. And since we know that every single multiple of 2 cannot be a prime number, then let's just go ahead and mark them all off. So 2 will be the longest one, but I'm going to go ahead and cross out 4, 6, 8, 10, 12, just anything in these columns. So I'm gonna loop starting from 2, and I would go all the way until 40. And I'm gonna go ahead and say everything that I've marked off is no longer a prime. So now that I've marked everything off, let's move on to the next one, right? So let's move on to 3. So 3 hasn't been marked yet, meaning that's a prime number. So let's go ahead and mark off all of 3's multiples as well. So 6 has already been marked, so we gotta do the rest. So 9, 12 was already marked off, so 15. 18 is done, 21, 24 is done, 27, 33, and 39. Um, so next we move on to 4. So 4 is marked, therefore it's not a prime. So we don't really have to do anything. So let's move on to 5. 5 hasn't been marked, so it's a prime number. Let's mark all of its multiples. So we have to get rid of 25 and 35. 6 has been marked, therefore it's not a prime number. And then 7 is not marked, so it's a prime number. Let's mark all its multiples. It'll be 14, 21, 28, and 35, which are all already marked off. And one thing to notice is that like 7 is a prime number, but when we try to mark all of its multiples, they're already marked, right? And the reason for that is let's look at like the factorization of some of these bigger numbers, right? So if we go ahead and look at 35, right? 35 is represented as 7 times 5. So what this means is the reason 35 is already marked is because we would have marked it when we did 5, right? So by the time we reach the bigger multiple, it's already going to be marked off. So using this property, we know that there's actually no reason to go past the square root of the biggest number in our range. So for example, the square root of 40 will be a little more than 6. So I know that I don't have to go and mark anything past like square root of 6, because if it was going to be marked by a number, it would have been hit by one of these smaller ones. Does that make sense so far? Also, no one said anything, but as always, if you have a question, just stop me. So does this make sense?
Yeah, you meant the square root of 40, right?
Yeah, square root of
The
40. I
oh,
don't know what I
okay.
said, but yeah, square root of 40 will be like, I don't know, like 6 point something. So I know that like 6 point something. So like if I go to like 7, then I know that like everything's already been marked. So like I
Okay.
don't have to repeat the process for like 8, 9, 10, and so on, right? Because once I reach this point, everything's already marked. So now that I've already successfully marked everything in this array, everything that's left is a prime number, and everything isn't that is marked is not a prime number. So what we'd want to do is there's a lot of like random things you could do with this. For example, like I don't know, like you would usually store this in a 1D array, right? So I know it's two-dimensional here, but it's because I can't draw to like the edge of the whiteboard. But you would have like an array of size like 40 like wide. So like if I want to go check if like a number is prime, I could like if this array is called is prime, I could just check if the value is like 0 meaning marked or 1 if it's unmarked. So does that make sense how you would actually code this? So like when you arrive at something, if it's like 1, like you could pre-initialize the entire array to ones, and if you land on a 1, then you mark all of its multiples as 0, and then if it's a 0, then you know it's not prime. So what we could do now with this array is we could, for example, like push it into a vector if it was unmarked, and now we have every single prime from 1 to 40. Does that make sense?
Yeah, I don't know how you would so you would make an array of booleans?
Yep.
Okay.
Yeah, and I was like leaving this as an exercise for you guys to code, but as always, I'll always be like giving you the code afterwards and going over it. But the reason I don't like going over this first is you don't really understand why this is important, right? So I can't like I myself don't even know why this is true, but the time complexity of this is n log log of n. And because there's a double log here, like this number is so tiny it almost becomes a constant. So let's say like you wanted to find if every number between 1 and 10 to the 7th was prime or not, right? So I'm gonna go ahead and pull up Desmos to do the math on that while my computer is lagging. So if I do like I don't know like 10 to 7th times log of. So this comes out, if n is equal to 10 to the 7th, how many items we're dealing with, and you plop this into this, you get, log base 2, you get 4 times 10 to the 7th, meaning that, like, it's very close to O of n, right? Because, like, O of n with n of this would just be 10 to the 7th. This is only 4 times slower, and since we can process 10 to the 8th operations in a second, we know that we can find if every single number between 1 and 10 to the 7th is prime or not. And we can usually, like, most of the time when you have a problem, like, with these very weird constraints, you know that you have to use sieve because if you use any other method, it'll take too long. So, as I mentioned, I'll go over the traditional method to checking if a number is prime or not, and I'll show you why it's slower than this, right? So if I go ahead and wipe all of this, let's try to find a more generic method of finding if a number is prime or not. So so as I mentioned earlier, a prime number is a number that can only be divisible evenly divided by 1 in itself. So let's look at 15 for example, right? So So one thing that we could do to check if a number is prime or not is like we know that only 1 and itself should divide it. So we could just check every number in between to see if it does. So I lied, I actually won't do 15. I'll do 7 once again because we know 7 is prime. So if I go ahead and draw every multiple out here, um Oops. We know that 1 and 7 are obviously always going to divide it, right? So we just need to write a for loop from 2 to n minus 1, and if any of these numbers divide this, then we know that it's prime, right? But the problem with this is the time complexity is of this is O of n, right? So you're always going to have to check 2 less than the value of your number, like different values, in order to check if it's prime or not. So like for example, if we were instead checking 43, you would have to check every number all the way up until 42, right? You would have to check
But
2 to 42 just to see if it's prime or not.
but
So
don't we have to
yeah.
check until the square root of that number?
Big little spoiler, but yes, that is the optimization. So in this case, right? Like we could simply, I got a magnet on here. So we could check every number between 2 and n minus 1 to see if it evenly divides it. But the time complexity of this is O of n, right? Just to check if one number is prime or not. So if I go ahead and write our like time complexity of sieve, um in here, so log n, and I compare it, and we know for each number it'll take O of n. So if we want to check from 1 to 10 to the 7th um numbers if they're prime or not, this would take O of n squared using this method right here. Does that make sense? So checking one number is O of n. So if we want to check all numbers from 1 to n, it would be O of n squared. Does that make sense? So if I want to find every number from 1 to 10 to the 7th, and I want to find if they're all prime, using this method, each number will take O of n. And since we're going through n numbers, it will just be n squared. So as Anj kind of spoiled, there is a shortcut, right? So like I mentioned with the sieve trick, um, we don't actually have to check every number from 2 to n minus 1. And the reason for that is if I go ahead and like draw 15 and all of its multiples, um, as earlier, like stop me whenever you have a question. So
Or
like
a spoiler?
if I do 15 here, right? So so we don't have to check 1, we don't have to check 5 because by definition, like every number like is divisible by those. So now we let's check if 2 divides 15, right? It doesn't, so we're good. Let's check if 3 divides 15. It does. So we by now we know the number's not prime. But if we go ahead and continue and check if 4 divides 15, it doesn't. Does 5 divide 15? It does. But the observation here, right, is that 15 is um composed of 5 times 3. So I don't actually have to go all the way until 5 to check if it's evenly divisible by something, right? Because in order for 3 to divide 15, like you have to multiply a number by 3 to get to 15, which is 5. So if you think of integers in terms of their multiple pairs, and what I mean by that is 12 can be written as like 1 times 12, 2 times 6, and 3 times 4. Um, you know you never have to check the bigger number because the smaller number will always tell you first if it divides it. So if we go ahead and think about what is the biggest value that you can possibly get if you take the smaller of the two, it's going to be square root n. And like it conceptually it should kind of make sense, right? Because for example, if we look at 49, 49 is represented as 7 times 7, and if you take the smaller of these numbers, it's just 7 itself, right? Meaning that like since we know we never have to iterate towards or, like once we find the smaller number in the pair, we're done. The biggest that the smallest number can be between the two is square root n and square root n. Therefore, you know that you never have to loop more than square root n just to check if it's prime or not. So just to give like a little recap, like um you do like want to know if every number between 2 and n minus 1 divide the number that you're checking is prime or not, but you don't actually have to check all of them. You only have to check until the square root of n because you know that the smaller number would reveal if it's prime or not before even getting to the bigger numbers. So in this case, square root 15 is like barely short of 4. Let's say like it's like 3 point something, or square root of 15 is like 3 point like I don't know like 8 something. So you know that like once you check 3, you're all done. There's no reason to check the 5 because the 3 already told us it wasn't prime. So does that make sense for primality checks?
Yeah.
Good. And once again, the time complexity now is no longer O of n to check if a number is prime or not, right? It's square root n. So once again, if we want to check if every number between 1 and 10 to the 7th was prime or not, we know that we have n numbers in total, so 10 to the 7th, and each number will take square root n time. So instead of n squared, we now have dropped it to n square root n time complexity. But if we still plug this number into like Desmos, for example, like I'll put 10 to the 7th times square root 10 to the 7th. Like I said for sieve, for 10 to the 7th, you get 4 times 10 to the 7th operations, which is less than 10 to the 8th, so it runs, right? But if we plug that in for our faster method of this square root trick, we still get 3 times 10 to the 10th. And if we can do 10 to the 8th operations in a second, and this is 300 times bigger, this would take several minutes to run, and like you would never be able to use this in a competition. So that's why it's so important to use sieve when like you're dealing with like checking a lot of prime numbers, because it's the fastest way for you to figure out like all of them, and it'll be the only way that you can like do these calculations in time. Does that make sense?
Yeah.
Sick. All right, and I only have one more thing left for today's lecture, and it'll be binary exponentiation. So this one isn't too bad, I think, but let's say you want to calculate 4 to the power of 8, right? And yeah, you could just use the PAL library, but in a lot of cases for problems, you'll basically have to like mod this number to get it to store in an integer, so you can't just use the PAL library. Like it just won't work. So you have to be able to write your own power function, right? So if you were to write 4 to the power of 8, the easiest way to do it, right, is to like have like so I'll call it res for like result. So you'll initialize something as 1, and then you'll loop from like I equals you'll just loop 8 times, right? Um and then you'll do like res times equals 4, right? So pretty easy way. If you want to get 4 to the power of 8, take a 1 and then multiply it by 4 8 times and it'll work, right? But the problem with this is that the time complexity of this is O of n, where n is your power, right? So like let's say for like some dumb reason you want to calculate 10 to the power of like 100, you would have to make 100 multiplications. But there's an optimization we can do for this, right? So one thing that we can observe is like using like exponent properties, a redraw like let's do like 4 to the 10th, right? So instead of like comprehending this as 4 to the 10th, we could rewrite it as 4 to the 5th times 4 to the 5th, right? We can break up the powers. So like I guess I can first write it as 4 to the 5th squared, which then turns into this. And the reason that like breaking it down into this format is so powerful is like why would we waste all of the time multiplying like for example, like we no longer have to multiply by 4 like so many times if we can just double it. So starting from 4 to the 10th, if we want to bring it all the way down to 4 to the 5th, it would take 5 multiplications, right? But if we just double it, then it only takes once. So what we're gonna do is instead of writing a for loop and multiplying 1 by like our base this many times, we're gonna have a protocol where if the power is even, we can simply square the number we have and cut the power in half. So let's look at the example of like 12, right? So let's do 2 to the 12. So if I want to calculate 2 to the 12, I have I'll put it over here. So my result starts off at 1. So if I'm at 2 to the 12, I can rewrite it as 2 to the 6 times 2 to the 6, right? And now what I can do is like so I'll just write it in here like stored into my answer. So for example, like what we can do is we know we have 2 to the 6th times 2 to the 6. Actually, I didn't really plan this out very well, but we can just leave it like this. So we know we have 2 to the 6 times 2 to the 6, but once again, the power is even, so we can break this up, right? Um, into 2 to the third squared, right? So now we can look at it as 2 to the third squared, I guess. And when the when the power is odd, we have kind of a dilemma, right? Because we can't turn like an odd power into this. So what we're instead gonna do is we're gonna pull out a multiple of it, and then we're going to just dump it into the answer and then continue doing it. So instead of going on with this tangent, I think it's best if I just do like a literal example. So let me think of something. Clearly I didn't have an example planned out. But let's say we're trying to find out what 2 to the power of 7 is, right? So 2 to the power of 7. So we know that we're currently at an odd power, so we can't like divide the power in two and square it. So we need to like pull aside a power of 2 because reducing this power by 1 will turn it into an even power, right? So what I'm going to do instead is I'm going to rewrite this as 2 to the power of 6 times 2. And because this is on the side, I'll just go ahead and add it into my answer. So now we can forget about this 2 because I've multiplied it into my answer, but we can now square our base and cut the power in half, right? So 2 to the power of 6 can be rewritten as 2 to the power of 3 squared, or it'll make a little more sense if I write the other way around. Um, so now we've broken the power from 6 into 3 in just one step, and we can just go ahead and make this multiplication of squaring the base. So now we're at 4 to the power of 3. Now, once again, we're at an odd power, so like we can't cut in half like an odd power, because then we'd just be like missing a number. So I'm gonna instead write this as 4 to the second times 4 to the first, and I would just multiply this into my results. So 2 times 4 is 1, and then now I don't have to worry about this. So once again, 2 is an even power, so I can go ahead and write it as um, 4 squared to the first, giving me 16 to the first. And now that I just have one power, I know that my answer is just 8 times 16. So a more like systematic way of thinking of this line is like if I have 8 to the 6th, then I shouldn't be wasting like 6 operations just to multiply this. I should just instead square the base and cut the power in half. So 8 to the 6th is equal to 64 to the third. So what we're gonna do now is whenever we want to calculate a very big power, we're going to have some result number like on the side. And if our power is even, we're going to square the base and cut the power in half. If the power is odd, so in the case of like, I don't know, 10 to the 7, we have to rewrite it as 10 to the 6 times 10 to the first. So we'll go ahead and multiply this into our answer, and then we'll cut the power in half on the next step. And by the time like you've reduced this all the way into 10 to the first, you multiply it by your result over here, and you've successfully calculated 2 to the power of like whatever, except instead of taking O of n time, we're cutting it in half each time, right? So let's say we do this process, but instead I do 2 to the 16 because I can actually manage that on here. So if we want to calculate 2 to 16, the O of n way, right, is to just write a for loop and multiply 2 16 times. But let's see how much faster this way is, right? So if I square the base and cut the power in half, I know that 2 to the 16 is the same as 4 to the power of 8. And then I'll do it again, right? This power is even, so I can rewrite it as 16 to the fourth. And then once again, I can do it again. So square the base, cut the power in half. So I have 256 to the second. And then if anyone knows what 256 squared is, be my guest. We have 65,536. And you'll notice that instead of multiplying 6 times, I only took log base 2 of 16, or it only took me 4 steps to get to my result, right? So using this method, we've we've reduced the time complexity to calculate a number to a power from O of n to O of log
Log.
base 2 of n. So this will be much faster. And I know it seems like a very weird thing to know because as I've told you, we can do 10 to 8th operations in a second, right? So this will only pay off if you're trying to calculate like 5 to the power of 10 to the ninth, right? But it is used in other things where it'll come in handy later on. But are we all good for this? Any questions?
Yeah, sorry, my mic was muted.
Oh, all good. So what's up?
No,
Oh,
it
you're all
makes
good?
sense.
All right, good.
Yeah.
So yeah, once again, the systematic approach of thinking of it is if the power is even, square the base and cut it in half. If it's odd, then just take your current base and multiply it into the answer, and then subtract one from the power, and then it'll turn even, right? So you'll just repeat this process until you get your answer. So that's all I've got planned. Obviously there's problems on these. So the first thing that I need to teach you in order to check that your uh like binary exponentiation makes sense is like for example, if I made you calculate 2 to the power of 10 to the ninth, it would overflow, right? You can't store this in an integer. So as I mentioned earlier, usually what they'll do in problems is they'll ask you to mod it with a number. So the number that they usually have you mod it with and that I will have you mod it with is 10 to the ninth plus 7. So what this means is if you print it like mod it with this number, it can start to fit into an integer, right? Because you don't have to calculate this entire answer. But the thing that you have to do is you can't just go ahead and like try to calculate 10 to the power of 9 and then at the very end mod it, right? So instead there's this property saying that if you go ahead and mod something in an intermediate step, it gives you the same result as if you modded at the very end. So for example, if we like wanted to calculate like 4 times 5, like mod 3, right? So we would do 20 and then we'd find the remainder mod 3, which would be equal to 2, right? But what we can also do is we can take 4 mod 3 and 5 mod 3 and multiply them. So 4 mod 3 times 5 mod 3, and I'll get 1 times 2. I get 2, same thing. So in order to check that your answer is correct without overflowing, you're going to have to mod with this number, but that doesn't mean that like you just try to do the problem the same way and then at the very end you mod, right? What I'm trying to tell you to do is anytime you make a multiplication, mod with this number so that it fits inside of an integer and then just print it at the end. So at every single step, anytime you do a multiplication, mod it with this so that it fits in an integer still.
Yeah. And don't you have to mod at the very end too?
Depends on how you do it. I mean, if you mod with every operation, then you don't have to mod at the end, right? Because the last operation you did was already modded.
Oh, but like what if you have like 5 times 7 and you're modding it with 2? Like,
Oh wait, yeah, yeah. I get what you're saying. So like, for example, like if you mod them both and then multiply, they can exceed the value of the mod. But I get what you're saying. I just mod it after anyways. So like
oh,
the way I would do it is if you're trying to take x times y mod m, what I would do is x mod m time there's parentheses around these times y mod m, right? And then like Anj said, multiplying these two can get the number like to overflow still. So you want to mod it again. I just do it in one line. So this is how I would code it. You mod x, you multiply it by y modded with m, and then you just mod it by, oh, sorry, there should be a mod sign here. You just mod it by this at the end. So I would do like z is equal to this. So that's how I'd actually code it. And if you do it this way, then you don't have to mod it like at the very end because like you're keeping it under M like after every single operation.
oh.
So all good. problems are already up. They're based on all of this stuff. This lecture was a little long, but we'll do solutions at, I don't know, we'll say 4. All right, so I'm gonna stop the recording.